So today we're going to talk about hybrid musical instruments. But before we do that, do you have any questions? I know that you're probably working on your assignment for Lab 3, and I'm pretty sure you have to do some extra soldering, you have to deal with sensors and all these things, so do you have any questions about that, or concerns or whatever, and of course you can come to office hours if you'd like to talk more about this, but any questions or?
I don't want to go too far down a specific thing, but one thing I was running into is getting the sensors, getting sensor information from the sensor through the TNC is working. And then like the Faust thing is working, but linking up how to get the Faust information and the sensor information to relate to each other. I wondered if there are like resources for where to find that, if that question makes sense at all.
Like your question totally makes sense, but I'm not really sure what else you need, like from as opposed to what you have on the lab website, because it's pretty it should be pretty straightforward, getting your sensor information and transmitting them to Faust, is there something specifically which is not working, or?
Yeah, that exactly what you just said, getting the sensor information, because I can turn it into like MIDI and send it as MIDI, but then if I'm actually in TNC Arduino.
Let me just share my screen, and I'm gonna try to re-explain that. Okay, so I'm gonna go on the course website. I'm gonna go in labs, lab 3. I'm gonna scroll down. Okay, so can you see my screen? Is it?
Yes.
Okay, cool. So so here you have analog read. Okay, and that analog read is reading values at port A0 on the TNC, where a sensor should be connected. And in the example of the lab, it should be an FSR, right? So so here in sensor value, you should get the value coming from the sensor, and that value should be a number between 0 and 1023, or something close to that. If you're not sure if you're getting this, you can of course use the serial debugging here to print the value that you're getting from analog read, right? So Julie, the values you're getting are correct, right? It looks like the sensor is working when you do this.
Yes.
Yes? Okay, cool. So once you have the value from the sensor, right, which once again should be a value between 0 and 1023, then you need to do something with that value and transmit it to the Faust portion of your program. Okay, so here I'm converting this value, which once again is a number between 0 and 1023, to a value which is supposed to be a frequency. Okay, and all I'm doing is I'm adding 50 to this value, to make sure that the lowest value I'm going to get for my frequency is going to be 50 and not 0. Okay, so here I'm basically just doing some super basic mapping. Okay, and then this is my Faust object, right? And so my Faust object is a Sawtooth Oscillator. it's the same Sawtooth oscillator as the one from the Teensy Faust tutorial. And okay, just to make sure that we are actually talking about the same thing. Okay, there is no link to it here, but if I go on the Faust documentation, if you go in tutorials, if you go in DSP on the Teensy with Faust, it's basically this code here, right? So that Faust program allows you to control the frequency and the gain of a Sawtooth oscillator. And the way you can control the frequency is by declaring a freak parameter, okay? And it's the freak parameter that I have here, right? And then on the Teensy side, all you have to do is to say set param value for freak, and then you just give it frequency, right, from your analog read.
Can I clarify that one line there, please?
Yep.
So that line, the freak, in quotations, that's referring to the actual the left-hand side of like what you're naming it in our the.
No. So basically, okay, let me open that in the Faust ID. Okay, cool. So basically, just to clarify things, because I think that's what your question is. There we go. So these are variables that you are creating in Faust, and then you're assigning a user interface element to that variable. Okay, so what do you access from the set param value method here? So basically what you access with this, the freak you have here, okay, is the freak that you have here.
Thank you. Yeah, so that makes sense now.
So it's the name of the user interface element, okay? And so basically, whenever you want to change the value of a Faust parameter on the Teensy, you have to call the name that you gave to that parameter in that field here. Okay, so if I wanted to change the gain with the FSR in that example here, I would just put gain in here, like GAIN, right, and not G.
I think that was my biggest thing. And the right-hand side is you're just renaming it. Like you're calling it frequency in the right because you created that float. And then if you want to scale something, you scale it in the, I'm sorry, I'm just clarifing. I hope this is helpful, Julie.
Yeah, no. I think this is helpful to everyone here.
Yeah. You scale that particular thing in the line before where it float frequency equals, because that's where you're doing it at the sensor value.
Yeah,
I'm talking out loud because I think I also I'm just not used to coding like this, so there's little things that are confusing to me. So I will come to office.
No, of course. And basically what you're doing here, like the float frequency equals sensor value plus 50, is something that you could actually do on the Faust side. As opposed of doing it on the Teensy side. Here I chose to do it on the Teensy side, just for the sake of the example. But you could have done that on the Faust side, and if you wanted to do that on the Faust side, maybe I could have created an FSR parameter, and that FSR parameter would have been maybe a default of 0, a minimum of 0, a maximum of 1023, and a step of 1, because those are integers, okay? And I could have called this FSR, and then I could have said F equals FSR plus 50, and so basically now I'm not doing the mapping on the Teensy, but I'm doing it in Faust, okay? and the result in the end is the same. So honestly, I think it's easier if you do the mapping on the Teensy, but if you want to do the mapping in Faust, you can do it in Faust as well. So
but in this case, how does it know which port it's reading? I mean,
how does it know what? Sorry.
the port, I mean, like, for example, right now, I think in the example you had A0, the analog pin where it's reading. If you do it in Faust.
Yeah, no, but in that case, you would have to
do the same
update
thing.
your set param value so that instead of using freak, it would be using FSR.
FSR. So the same code. Can I ask you a quick question regarding the photoresistor? I got values like they varied. They had a range much smaller than, for example, the FSR. Like, that's for example, like if it was normal light, it would be 600, and then if I put my finger on it, 400, and if I shine the my iPhone, that would go 800 tops. It never reached the max. Is that normal?
Yeah, it's normal because you know, like the range of the photoresistor is pretty wide. So it's really designed for a wide range of amount of lights, basically. You know, like so if you wanted to get like the maximum, say 1023, like you'd probably need a lot of light, like more than what you're getting with your phone, basically. You know, like so if you bring it outside, you know, and point it towards the sun at midday, then you're probably going to reach a higher value than if you're doing it with your smartphone, right? So basically, with that kind of sensor, I mean, using photoresistor is always kind of tricky because depending on where you use them, they're not really going to behave the same way, right? So if you use them in a very dark room, you know, like they're going to be like they're going to behave very differently than if you use them outside, for example, right? And so but if you want to use them in a dark room, you know, like usually you have to do some mapping where you basically expand the range of the sensor by, you know, like saying, okay, I have a value between 200 and 600, you know, and now I'm just, you know, subtracting everything by 200 and multiplying it by 2 or 3, you know, like so that I get a wider range.
Yeah, you have an example in on the
there we go.
On the web. So, and the other question I had is regarding the resonant low pass filter that you recommend we use. I did it like, you know, just brute force with the FSR, and of course at 0 it kind of dies out, and even after, if you give it values, it still stays dead.
Well, so the best way to make sure that this doesn't happen is not to
add a value, of course. But I was wondering if you have some, the design is like it doesn't recover when it starts from 0, basically.
Well, yeah, you know, the problem is that you know, it's a resonant filter, and so if you give it a value of 0 hertz, there is probably no safeguard in the implementation of the filter, so that if you give it a 0 value, like the poles go on the unit circle.
Absolutely.
And once the poles went on the unit circle once, then the filter becomes unstable, and it will probably remain unstable for forever.
For the rest, So good to know.
So you know, like Faust is, you know, like once again, you know, like Faust is lower level than what you would get in Pure Data or Maximus P or like you know, like so like it's your responsibility to not give weird values to some of the parameters you're changing with like with Faust, basically. You know,
that you learn very quickly, I think. Good, thank you.
Sure.
Can I ask a more general question, or do we need to go on with the lecture because we're running out of time?
More general question, please.
Yeah, just like I'm struggling with trying to make the sound good in the instrument. Like I don't know what I'm doing with music at all. And I'm wondering what kinds of things do you suggest we try in Faust to kind of like really change the sound of the instrument? Like we tried the resonance low pass filter. There's effects. there's like making sure you don't give it weird values that you just talked about, but like what kinds of things can we try to kind of make the sound either more interesting or sound better to our ears?
It's a very tough and good question that you're asking. There is obviously like no like short answer to this question, but you know, like usually, I mean, it's hard to tell like what makes an interesting sound, you know, like, but usually like a sound will be interesting if it evolves in time, you know, like, so if your sound is like completely like static, you know, and it's just like a bah, you know, like a note that starts, you know, and then just like remains the same, like then it's probably not going to be a very interesting sound, like, so you want to create sounds which are evolving in time, you know, and there are many ways for doing this, you know, and typically like using like an effect is not necessarily the best way to do that, you know, because an effect is gonna change like the timbre of the sound, but it's not gonna like make sure that your sound is actually evolving in time, right? Because you know, like effects are usually static, you know, like they're not gonna like they're gonna change like the spectrum of the sound, but they're not gonna change the spectrum necessarily like very dynamically, basically, you know, like your sound is not gonna have like a life, basically, you know, and so if you want to create sounds that actually change, you know, like one way of doing it, you know, is to do it like in the example in the first lab, you know, like where you map some of the parameters of the sound synthesis algorithm to an envelope, you know, like so that they change in time, you know, like, or to a sensor, you know, like, I mean, like if it's a continuous sensor like an FSR, then you're going to be able like to change the parameters of the sound in real time. And typically you want to use a sound synthesis algorithm where you can do that kind of stuff, you know, and another example is our physical models, you know, and let me share my screen with you, because I know that some people asked some questions about that, and okay, so I'm sure you tried that at some point, you know, because I think it's part of the examples, but in the physical modeling library of FAUST, right? Like PM is for physical modeling. If you look for violin UI, okay? So if you tried that, and if you actually ran it, okay. So in that case, the user interface, you know, I'm sure you already know about that, you know, because that was part of lab one, you know, like, but in that case,
yeah, I think I was mostly overwhelmed by how complicated the violin was, and also that it was like in a different structure than the programs we looked at previously, because it had like internal variables.
Well, of course, yeah, but let me just like show you what I mean here. So so basically so that instrument has multiple parameters that you can control, you know, like, but it doesn't have any trigger, right? Like there is no like button to start the violin or stop the violin, right? And the reason for that is because it's a physical model, you know, and because it's a physical model, you can control physical parameters of the instrument. And for instance, here in the bow section, there's a velocity parameter. And the velocity parameter is the velocity of the bow on the string, okay? Currently, it's set to 0, so there is no sound because you're basically not moving the bow, you know? But like whenever you're gonna start increasing the value of velocity, you know, you're gonna get more sound because you're basically bowing the string faster, right? Or slower. And you can also change the pressure, you know, and pressure is basically literally just like the amounts of pressure you apply on the string as you are bowing the string, you know, and you can also change the position, you know, like which is the position of the bow on the string. So that instrument here, like this physical model, if you just like give it like static values for bow, pressure, velocity, and position, it's going to sound very dry and very boring, you know, like very, yeah, definitely uninteresting, you know. But if you start to control these three parameters in function of each other's, using sensors, for example, you know, like say an FSR and maybe a knob, for example, to control like two of those parameters in real time, then it's going to sound way more interesting, because it's actually going to start sounding like an actual violin, you know. And so what I'm trying to say here, and it's good that you're asking this question because it's related to today's lecture. But what I'm trying to say here, you know, is that especially if you deal with physical models, or if you deal with synthesizers, which are complex enough so that it's not just a question of like pressing a button to start a sound, you know, and then releasing it to have no more sound. Usually with that kind of synthesizer, one thing that matters a lot is the way you control them, you know, and the way you control parameters in function of each other's. And if you think about it, you know, like that's how real musical instruments work. You know, if you take a real violin and the amount of pressure you apply on the bow, on the string with the bow, is not done in function of the velocity of the bow, then you're probably going to get like a horrible sound, you know. And so what I'm saying here is that you really need to control these parameters in real time with continuous values and in function of each other's, you know, and then only then you will actually get something that sounds actually reasonably good, you know. And just to finish on that, you know, because I think it's a very interesting topic. So so just to show you like an example of what I'm trying to say here. I'm going to show you a project that I did a very long time ago. It's on my website, and if you scroll down, it's like at least 15 years old. Shit, where is it? Okay, the Faust SDK. Okay, so if you go in here, and I'll paste the URL in the chat once I'll be done. Okay, so here you have audio examples. Okay, and in the audio example section, you have the last example, which is called Munera, and so that example was actually synthesized with the exact same physical model as the one from the violin that sounds so dry and so boring in here. Except that what we did is that we actually took a real violin player, we put motion sensors everywhere on the bow and on the violin player and on the violin. And from that, we actually computed values for the bow velocity, for the bow pressure, and also for the bow position to control these values in real time, you know. And if you play it, you'll see that it actually sounds pretty good, you know. It actually sounds like a violin, as opposed to the very dry example that I just played. And so this is I don't know if you'll be able to hear it. But so, you know, it's not the best violin in the world. Like, you can still tell that it's a synthesizer, but it's better than this, right? Where you know, like in that case, it just sounds like another like random shitty synthesizer that you've made in Faust, you know. Like, but here, in that example that I just showed you here, it actually sounds good, and they're just the same models. It's just that they're not controlled the same way. And in one case, you have static control, and in the other case, you have dynamic control. And so for now, I think that's really just the best answer I can give you.
That's super helpful. They give me a lot of places to start. Thank you so much.
Sure. Okay. So I'll just put the URL here. There we go. Great. Any other questions or? Cool. So today we are going to talk about hybrid musical instruments, combining physical and virtual elements. Okay, so this is kind of a weird topic and a weird lecture, you know. Like, so if you were to take this class somewhere else, you would probably not necessarily talk about that, you know. Like, but I worked a lot on this topic, you know. Like, so I felt like I actually needed to give a lecture about this. Okay. Great. So we already kind of talked about this a little bit at the beginning of the quarter, but this is the digital musical instrument. Okay, and so why am I saying that? Like, why am I saying that this is the digital musical instrument? You know, it's because usually when you think of a digital musical instrument, you know, and if you remember the definition from Marc Battier, from what a digital musical instrument is, and that's something we talked about during the first lecture. And the definition is that a digital musical instrument is an instrument where control and synthesizers are two separated entities, right? And so that's what you see here on the screen, right? Like you have a keyboard connected to a computer, which here is acting as a synthesizer, probably playing a trumpet sound. But there are like two separated entities, like two different things, you know. And so there are, of course, pros and cons related to that. And in fact, like maybe we can actually talk about this, you know, like so can someone tell me, like, what do you think like the advantages are of having an interface separated from a synthesizer? Like, what are the advantages? Like, what do we get from this? Like, from this kind of model? This is a question. So why would we want to do that? Like, what are the advantages?
Your interface can be hooked up to other like synths then?
Yes. You know, and the other way around too, right? So basically the main advantage of doing that is that you end up with a completely generic system, you know, like, which is a keyboard and a synthesizer, and you can control any sound with an interface, which is an interface that a lot of people know already, you know. And a piano keyboard is a very common interface, you know, like a lot of people know how to play the keyboard, you know. It's a very practical interface, you know, like so on the paper, it's a great idea, you know, because it means that if you know how to play the keyboard, you can play any instrument, basically, you know. And that's really the main thing that synthesizers in the 80s like tried to sell to people, like to musicians, you know. It's like if you know how to play the keyboard, then you can play any sound, you know. And in the head of a lot of people, when you think about synthesizers, that's what it's all about. And the other, it's true, like the opposite is true too, you know, like it means that if you have like an other interface, you know, like the EWI interface that we saw during the first lecture, which I don't know if you remember, you know, but it's a woodwind instrument interface. It means that from that interface, you can also like play any instrument, you know, like so there is always this question of skill transfer as well, you know, because if you know how to play this interface, then it gives you access to all the instruments, you know, like so that's mostly the main advantage of this kind of model. Now, can someone tell me what the disadvantages might be? Like, what are the cons basically of having this kind of model here?
It makes you interact with it. Oh, sorry.
I was just going to say, feel free to unmute, but also, guys, if you want to use the raise hand feature, that can help too.
Julie, you were about to say something.
It makes you interact with the synth in this kind of standardized way, like what you're saying with the violin. You know, you're controlling it in a way that like a trumpet isn't actually usually controlled.
Absolutely. And that's the main disadvantage of using this kind of model, you know. So if you play a piano sound with a keyboard, it's going to work great, you know. And in fact, I don't know if many of you used synthesizers like this, you know, in the past. You know, like for those of you who are keyboardists, you know, like, but usually the piano sound is always the one that sounds the best, you know, on those like I'm mostly talking about like cheap synthesizers, you know, like, you know, and it's because like in the case of a piano, the interface that you use is exactly the right interface to control that instrument, you know. And in the case of a piano, when you start a note, you know, like you activate the note, boom, you know, and then it decays in time, you know, but the frequency of the note doesn't change, like the pitch remains the same, right? And if you want to kill the note, you just have to release your finger. But in terms of control, you have very, 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 very little control on the spectrum of the sound, on the timbre of the sound that you're producing in the case of a piano. And as humans and as musicians as well, we are used to that. We know that piano sounds don't evolve in time, you know, like, so that's why when you get a cheap synthesizer, the piano sound always sounds good, you know, because it's not necessarily hard to synthesize, you know, and the interface you're using is perfectly adapted to this, you know. On the other hand, if you think about the trumpet, you know, for those of you who play woodwind or just like any wind instrument, basically, you know, like there's so much that is happening in your mouth, you know. Fingers, you can do stuff like to control the way sound is going to happen. Like in the case of the trumpet, you know, it's the pistons and also the slide, you know, like, but it's not really going to change too much the way it sounds, you know. But in your mouth, like, and in the case of the trumpet with your lips, so much is happening, you know, like depending on the tension of your lips, the pressure in your mouth, you know, like, you know, these parameters in function of each other will completely change the way you perceive the sound and yeah, and how the instrument in general sounds, basically. And the problem is that with this interface, with the keyboard interface, you don't really get that. Like you know, once again, you know, like once you press the key, you start the sound, you know, and but you have no way to control what I'm talking about here. And so, you know, we have a guest lecture by Jordan Rudess at the end of the quarter, and Jordan Rudess is known like by many people as like he's a very famous keyboardist, basically, you know, and he completely masters, like, and we can ask him to show us that, you know, like during his guest lecture, but there is one thing that he completely masters, and it's the pitch wheel that you have here on those keyboards, you know, like, so basically, like the two wheels that you have here, you know, like, and it's a very standard thing, like one allows you to bend the pitch, you know, like, so basically you press a key, and then that wheel here is always centered on 0, and there is like a spring, you know, that always brings it back on 0, you know, like, so you can actually push it forward, or you can pull it, you know, and if you pull it, you shift the pitch down, you know, like, so if you're pressing the key to ba, and then ba, and then if you want to pitch shift up the pitch, you know, like, then you just have to push it, so, you know, ba, you know, something like that. And so there are some keyboardists that actually learn how to deal with that, you know, and Jordan Rudess is one of them, you know, and he really can play a trumpet sound using that. But when you see him playing, it's actually crazy, you know, because it goes so fast, you know, like it's really like a skill that he learned, you know, like to pitch shift the notes that he's playing using this pitch bend wheel on the keyboard. And but it's not super practical if you think about it, you know, like if you like from a human computer interaction standpoint, like this is like a very like engineering oriented solution, because you're like, okay, I need to bend the pitch, you know, like, so I'm going to add a wheel, you know, and I can play it with my left hand, you know, like, but it's not necessarily super easy to use, you know, like, so all I'm saying here, you know, is that for like this model, dissociating the interface from the instrument usually breaks the connection between the two. And even if you try to use techniques to make things better, like the pitch bend wheel that I just talked about, in many cases it doesn't work, you know, because those two things are broken. And that's not a problem you have with traditional musical instrument. Like with a traditional musical instrument, usually, and I mean like an acoustic traditional musical instrument, the place where sound is produced is the same as the place where you control the sound, right? If you think about a guitar, on a guitar, strings actually play the sound, and they're the source of the sound, but you interact with them directly. So they're also the interface, right? And a guitar sounds good. It's a good musical instrument, probably for, well, in part for that reason. And so, so the first person who kind of noted this in the field of music technology is Perry Cook. And I'm sure at this point, most of you know about Perry Cook because you read part of Gaz's book. But Perry Cook says that DMIs are often demutualized, and this is a super weird word. You know, like I think he's kind of the only one who used that word. You know, like, but demutualized, you know, it's like they're not mutual, right? So they are separated, resulting in a loss of intimacy between performer and instrument. Because, you know, that's what a musical instrument is all about. You know, it's basically an extension of your body in a way, you know, and the interface is what creates the link between this extension of your body and your body, right? And in the case of this instrument, sometimes the connection between the interface and the instrument is kind of broken because they are not necessarily compatible with each other's. And that's what I wanted to talk about today. So in the world of digital musical instruments, there are a couple of instruments that try to solve this problem, if we can call that a problem, by creating hybrid instruments. So instruments which are both acoustical instruments, but also digital musical instruments. And I think the first commercial example of that, and we already talked about it during the first lecture, but you know, now that you know more about the DMIs, I think it's good that we talk about it again, is the Korg wave drum. So the Korg wave drum is a very unique digital musical instrument in the field of music technology. You know, it's probably the only example of commercial product of a hybrid instrument, as I just spoke about, you know. And so what it does is that you have a drum membrane, you know, and so that's the membrane here. So it's just like a real drum membrane, you know, like, you know, it's probably made out of skin of something, you know, like, or, you know, like drum membrane, and then you have a frame. Okay, the frame is not really doing much, you know, but inside the instrument, you have a small computer which is acting as a sound synthesizer, and it basically gets the sound from the membrane. So there are contact microphones on the membrane, and that's what we're going to use for Lab 4. Okay, and those contact microphones basically capture the sound that you make on the membrane, you know, like, so just like with a piece of paper, you know, like if you touch it, you make sound. So there are contact microphones that actually pick up the sound that you make on the membrane, you know, like, so if you like rub it or if you tap it, the sound is going to be different, right? And then these acoustic excitations are going to be fed into digital resonators or digital physical models, you know, and in the starter codes from Lab 1, like the Faust starter codes, you know, there are string physical models, for example, and those are basically just resonators, you know. So basically, if you feed the sound that you get on the membrane to one of these resonators, then it really sounds great. And exactly for the reason that Clara asked about earlier, you know, like, which is basically the resonator part of the instrument remains the same. You know, it's like if you take my plastic bottle here, like if I tap on the bottle, it makes a sound, but the the shape of the bottle doesn't change in real time. It's a linear system, right? So it's a system that doesn't change. Like so my bottle can be represented as a synthesizer of which the parameters don't change in time. Like what I described earlier. However, one thing that is changing in that case is where I tap on the bottle and with what material I'm tapping the bottle. So if I tap the bottle with my hand, it makes a specific sound. Now, if I tap the bottle with a screwdriver, then the sound is different. And so there is always a lot of complexity in the sound excitation that you are using to drive a musical instrument. And so that's what the wave drum is trying to take advantage of, and it's basically that it captures the sound of the excitation that you make on the membrane with whatever material you use for that. And then it feeds it into a digital resonator, like a digital synthesizer of which the parameters are static and don't change in real time, But it's going to sound amazingly natural because every single excitation is going to be different. Like every single sound you're going to make on the membrane is going to have like some small differences in its spectrum. And so just like a real musical instrument, every time you're going to produce a new sound, it's not going to sound exactly the same as the sound before, basically, right? And so let's watch a video of someone playing the wave drum, just so that you sort of get an idea of what we're talking about here. So it also has pressure sensors, right? FSRs. It's a Harpustron. That's what it is, So it's the string physical model that you have in your starter code for Lab 1. So like when you strike a membrane, when you strike the membrane at the center of the membrane, you tend to get more low frequencies in the sound that you generate because the lowest mode of the membrane sort of vibrates like this, and that's one that has the longest wavelength. Right. And so when you hit the middle of the membrane, you really push the membrane like this, so you really like drive that low frequency mode. On the other hand, like if you strike the membrane on its edge, like on the border, then you tend to drive more like higher frequency modes, because the higher frequency modes are the one that have like shorter wavelength, so you hit them better when you're on the edge of the membrane, and so here you get that in the sound that this guy is actually producing when he's playing the instrument. So like when he strikes the membrane like at the middle, he starts to get more low frequency in the sound, just like in a real drum, right? And then like as he goes closer to the edges, then he gets like sound that has like more high frequencies, or at least less low frequencies, and that's what we hear here in the example. So I don't know if these sound examples are the best, like for that instrument, but at least they demonstrate, I think, very well, like what this is all about, basically. like from a musical standpoint, I don't know if that's necessarily a good thing, but like at least you know like what I'm talking about here. And so for those of you who will have the chance to actually go to CCRMA one day when it will be open, there is actually a wave drum in the entrance. Like when you walk in the building, there is a museum with many old digital musical instruments, and there is a wave drum, and it's actually one of the prototypes, because the wave drum was actually developed partly with CCRMA. And so there is a prototype of a wave drum in that museum, and it's not in a very good state, because I think someone played it a little bit too hard at some point, and I think there is a hole in it, but it still works, like so you still get like the point. So do you have any questions about that, or like do you understand like what I'm saying, or is it like completely like abstract? Okay, cool. I'll take that as a yes. Okay, so after the wave drum, other people started to think about this idea, of using sound excitations to drive digital resonators, to drive virtual instruments, like which are resonators. So Ed Bertle, I think, is probably the next person who did that, and Ed thought that, if it worked with the wave drum, and if it worked so well with the wave drum, it would probably work very well with the guitar as well, because, a guitar, which is a plucked string instrument, from a physical modeling standpoint, is very close to a drum, because it's a percussive instrument. It's an instrument where you sound an excitation to drive some kind of resonator, and then the resonator dissipates the energy in it over time, and then sound just decays, and so whether it's a string or it's a membrane, like basically the amplitude envelope of the sound you are going to generate is going to be very, very similar. And so what Ed did here is that he kind of massacred this poor electric guitar by removing almost all the strings, as you can see, because it only has 2 strings left. And what he did is that he actually damped the string, and I'm not really sure why he used this material for that, and it does look kind of ugly. But what it's doing is that it's really just damping the string, so that basically when you pluck this string here, you only get the sound excitation of your finger plucking the string on the string, So basically, like when you pluck it, it's just make like, and basically what he does is that he takes this sound and then he feeds it into a physical model of a real string to control it, and it's the same idea as the one with the wave drum, where there is so much complexity in the sound excitation, because every time you're going to plug the string, even if it's at the same place on the string, it's always going to sound slightly different, and so you're going to get this complexity in the sound that is then synthesized, because the model is going to be driven in a different way every time you're going to plug the string. So in his instrument, what he did is that you basically used 1 string for plucking, okay, and 1 string for controlling the pitch. And so here, if I remember correctly, I think he was sending an electric signal in the string, like a very low electric signal. The goal was not to electrocute the person who was playing the guitar. But then each fret was actually connected to a pin on a microcontroller, and then he would know like which fret he was pressing through the electric signal, connecting the string, like to the fret, basically. So 1 string for plucking, clack, 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 and then 1 string for controlling the pitch, and so it's a very interesting thing, so I don't know if there is really a point of doing that, because you know, in any case, a real electric guitar is probably going to sound much better than his weird tuned electric guitar connected to electric guitar physical model. But you know, as a proof of concept, I think it's a very, very interesting instrument that he made. You know, and very close in aesthetic from the Korg wave drum that we just talked about. Okay. A couple of years later, Dan Moses, who also was at Karma, and I think the picture was probably taken on the Karma stage, here created this instrument as part of a Music 258 project. So it started in Music 258, but then he improved it in an independent study, I think, you know, so that's not like a final project for Music 258. It's a little bit more advanced than this, you know, and so Dan basically used this very interesting principle. So like you're probably thinking, okay, well, like, what is this and what is this? Because those two things are not the same. It's just that a couple of years after his first Cadichord, Dan actually made a desktop version of his Cadichord, and using exactly the same principles as the one that he was using here, but you know, like as a desktop instrument. And so basically, what he does in both cases, you know, like whether it's here or here, is that he's using plastic tines. You know, like and in one case here, it's basically I think it's polycarbonates. Yeah, it's just like polycarbonate that he basically cut. He cut with scissors, and then at the bottom of them, like below that, there is a piezo, a contact microphone, like the one that you have in your kit, and we're going to talk more about that when we're actually going to talk about the lab for this class. And the contact microphone is glued to the plastic plate, right? The plastic tine. And whenever he's going to like touch it, he's going to create sound on that plastic tine, you know, and it could be just like on a sheet of paper again, you know, so just like this, right? And the sound of the excitation that you create with your finger or whatever you are using, could be like a pluck as well, is then being sent into a string physical model. And in the initial version of the Cadichord, Dan was actually using Piezo Films. So what are Piezo Films? I just want to show them to you because they're actually not parts of your kit. I'm not sure we're gonna, yeah, there we go. Actually, that's what I was looking for. So basically, Piezo Films are contact microphones. Okay. Just going to close this. I'm going to open this one. Okay, sorry. This is a pretty low resolution picture, but they all look like this basically, right? So so there are these little, yeah, there we go. There are these little piece of plastic with piezo electric crystals in them, you know, and you can twist them, you can bend them, and they're great plug sensors, basically, you know, because you can actually use them as a microphone, and whenever you're gonna like plug them, you're really gonna get the sound of the pluck of your finger on them, you know, and there are no Piezo Films in your kit, but you know they're fairly cheap, and you can order them on the web, you know, if you wanted to do a project with that, you know, and so. So what happens with the Piezo Films when he plugs them? So let me play this video, and I think you'll get a better idea of what this instrument is all about. Anyway, I think you get the idea, you know, like, and here he's using a string physical model, and at this point, you're probably like, wow, it actually sounds pretty good. You know, it does sound like a string instrument, you know, and why didn't you give us physical model of strings that actually sound that good? You know, like, well, the answer is I actually did, you know, because the physical models he's using here are very, very, very close to the ones that are part of Faust and that are part of your of the starter code for Lab 1. And except that here, he's using them with real sound excitation. So they sound much better than the dry impulse that we're just sending in them like otherwise. And so there are a couple of interesting things to note about this instrument here, you know, like, but I don't know if you noticed, but the plastic tines in this version of the Cadichord have a kind of a weird shape, you know, like you can sort of see that, you know, like some of them are, yeah, there we go, you know, like they're kind of going in two directions, you know, and they go up, you know, and then down, you know, like, can someone guess why he did that? Like there is a reason for it. No ideas?
Downstrum and upstrum, or up? What's it? I don't know. Is that it?
Nope. No. That actually, that's a good that's a good thought though. You know, because whenever you're doing this, you know, like because you're well, but here, you know, like there is actually one string mapped for each plastic tine, you know, like so if he's strumming up or down, you know, like I mean he's still gonna get that with the instrument, you know, like but there is a reason why they have this shape actually, and it's related to what I said earlier. No? Okay, so basically it's just like on the drum membrane. On the drum membrane, when you hit the drum membrane at the middle, you're going to get more low frequencies than if you hit the drum membrane on the edge, right? And so here he tried to reproduce this by giving this sort of weird shape to the plastic tines, you know, like so basically if he plucks the plastic tine in the zone, which is like very thick, he's going to get more low frequency than in this zone here, you know, like where there is only like a little bit of plastic like popping out of the body of the instrument. And you know, with real string instruments, you're getting that as well, depending on where you're plucking the string. You know, like it sounds different if you plug the string near the bridge of your guitar than if you plug the string at the middle of the string, you know. And so he basically tried to reproduce this this effect here. And then for the left hand, the interface is super basic, you know, like this is just a keyboard basically. Like I mean, there is nothing like super interesting to say about that. You know, like I mean, all the interesting part of this instrument really happens with whatever he's doing with the right hand and the strumming. So so at some point, I think he wanted to make a startup, and then he had a kid, and he had a pretty good job, you know. And so it was like, okay, I'm probably gonna continue doing what I'm doing, you know. Like, and so he's a very nice guy, you know, and I'm sure like if you're curious about this instrument, like you could write him, like he'd be very happy to answer your questions. And he's based in the Bay Area, so he's pretty close if you want to meet maybe at some point. Cool. So so this is another example of this kind of instrument, you know, and that one is a commercial product called the Atv A-Frame. I think it's very expensive, and it's basically very similar to the wave drum. Except that the interface is bigger, you know, and the sounds are probably like better tuned, you know, like, you know, and it's a more recent instrument, you know, like so. But the principle is the same, you know. It's like a membrane with contact microphones on it, and digital resonators embedded in the membrane to produce the sound of the instrument. anyway, you get the idea, you know, like it's and so once again, you know, like the idea is the same as the wave drum, you know, it's like contact microphone, FSR, pressure sensor for when you're actually pushing in the membrane to get like some control on the sound that you are generating. But like the interesting part here, you know, is once again the fact that you're getting the excitation and sending it to the digital part of the instrument. Once again, you know, like this lecture is about like telling you that there are some digital musical instruments which combines physical acoustical elements to digital elements, and that usually this kind of instrument succeeds well as an instrument, you know, because they are mutualized to retake Perry's world, you know, and here is another example. That was a startup. I think it failed, you know, and they're not selling that anymore, you know. Like, but here they kind of had a more like bare metal approach to this, you know, like by providing a contact microphone that you could put like on any table, and then plugging it to an iPhone, where the iPhone here is acting as the synthesizer. And so you basically capture the sound that you make on the surface on which the contact microphone is placed, and you use these sounds to drive digital resonators working in the app. So and so I think in this version, he's not even using a contact microphone. I think he's just using the microphone of the iPhone placed on the table. So the cool thing about that instrument, you know, is that it's fairly well tuned, you know, and the sound that he's producing are actually pretty cool, and so, you know, it's always the same idea, and basically your lab 4 is going to be about making an instrument like that. You know, it's going to be making a hybrid instrument where you use a contact microphone, you put it on some kind of surface, you hook that up to your Teensy, and then you try to build an instrument using this principle, you know, and usually like that's an assignment that people like, you know, and because it's very convincing, you know, and usually that's when people realize that they can make pretty good sounds using what they have in their hands, you know, like for this class, you know, like so anyway, here's another example, and we already talked about that one. It's another product which is very, very similar to the impactor that I just showed you. You know, it's called the Mojis, and it's basically a small contact microphone that you can put on any surface, and you connect it to an iPhone app to synthesize sound. You know, it's basically the same idea. Allows you to transform. Well, anyway, so so the other thing that this one is doing is that there is some machine learning, which is mapping the spectrum of the sound that you generate to physical parameters of the synthesizer. You know, like, so basically they know if you put the piezo on an object, like the T thing here, you know, like they will know probably like if you open it or if you touch it on the side, you know, like so that's already like, you know, like 1 parameter, 2 parameters, you know, and same thing if you're on a table, like if you put the contact microphone on the table, they'll probably know where you're striking the table. Like it's not going to be super precise, you know, like, but precise enough so that you can probably do some mapping with that, and so that's an added value to this example. Here's another example. I'm not going to talk too much about that one, because it's yet another one, but just to show you that a lot of people actually try to exploit this idea. And Ali Momeni is a professor at Carnegie Mellon University, teaching very similar class to the one that I'm teaching here. And basically, this is an interface that he made. Well, it's more than an interface. It's a musical instrument that he called Caress. And it basically uses exactly the same principles as the one that we've been talking about. Like each of these little plastic plates have different textures on them, and you can see that they're actually mounted on these sponges, to basically insulate them from each other, so that when you're touching one, the sound that you're making on it is not contaminating the neighboring plate, basically. And so all these textures create different sounds, and just like cardboard sounds different from plastic, like when you rub it. And then when he was hooking this up to a computer with digital resonators, like he would be able to drive them using these things, and here's a demo of this instrument. Anyway, you get the idea. Cool. All right, so I actually worked a lot on this, and I made a lot of instruments that also use this principle. And this slide, if you want to look at it later, kind of gives you an overview of some of the instruments that I've made, and that kind of use this principle of using sound excitations to drive digital resonators. And the first one here is on the top left corner. I'm not going to talk about all of them because I don't really have time for that, but it was actually my 258 project from 10 years ago. And it was installed in the Karma Lounge, in this geodesic dome that we made for the performance. And then you had this cube, which was hanging from the dome, running physical models, and depending on where you would hit the cube, or touch it or rub it, you would get different kind of sounds that would be produced, and the cube was hanging from the middle of the dome. Anyway, if you're interested in that, you can actually look at these examples, but I don't want to talk too much about that because I'm kind of running slightly out of time, and that was not really the point of this lecture. It was just to sort of give you an overview of what people have done for that kind of things. So this is the last one that I've made, and I think I already showed it to you during lecture 1, but it's called the Blade Axe. And what this one is doing is that there is an iPad. The iPad is actually running a Faust string physical model on it. And you can use the touch screen of the iPad to control the pitch of the sound that you are producing. And then with your right hand, you have a system which is very close to Dan's cuticord system, where you have these plastic tines that you can pluck. And when you plug them, you can basically you basically create a sound, and that sound is fed into the physical model running on the iPad. So on that instrument, there is no sensors or Arduino or something like that. Sound is synthesized on the iPad, and everything that is coming from the body of the instrument is just sound, basically. It's really just the sound that you make with this that goes into the iPad. And just like Ali's Caress, you have this plate here, which is a pick guard, but that one has different textures which are laser engraved on it. And you can rub them, you can touch them, and they all make different sounds, and you can actually play with that. And so this is a bad demo video of me playing this instrument, just so that you get an idea. There we go. I tried to play blues, but I was not very good at it. Anyway, that gives you an idea, but you can make like pretty crazy sound with that instrument. And I'm not sure if I'm doing this here. Yeah, there we go. Anyway, so it's pretty broad, you know, and it's still the physical model, but except that in that case, it's kind of tortured so that you get that kind of sound. Anyway, that's it for the lecture. You know, like I can take questions just a little bit after that, but before I leave you, I just want to briefly talk about Lab 4. No, Lab 4 is not assigned yet. But I think it's a good time to talk about it because it's completely related to today's lecture. So, and I know that you're probably just starting to work on Lab 3 and the related assignment, but you know, Lab 4 is going to be assigned on Wednesday. So, so I think it's a good time to talk about it. So basically, in Lab 4, we want you to create a hybrid instrument, and you're going to have to follow all the steps of the lab before you can actually do the assignment. Okay, and you will just do it on your own. You're like, this time I'm not going to walk you through the steps of doing this, but basically, here's what we want you to do. You know, like we want you to find a sound source. So it can be anything. You know, it could be a plastic bottle, it can be the floor, it can be your bike, it can be a window, you know, a mug or whatever. Just find a sound source. On that sound source, you're gonna put a piezo, which is a contact microphone on it, and then it's gonna go through the Teensy audio shield, and then through a Faust resonator, and then maybe some audio effect. Okay, and then back to the sound output. You know, like that's basically what all the instruments that we talked about are doing. So in order to be able to do that, you're going to have to get the piezo from your kit. And it's basically this thing, and there are actually two of them. There are two of them so that if you screw one up, you get a replacement one, because it's very easy to screw them up. That's why I'm saying that. So anyway, so then the next step is basically to use the jack, like the male jack wire that you have in your kit. You're going to have to cut it, and then you're going to have to solder it to the piezo. Okay. And so that eventually you will be able to connect it to your Teensy. Okay. There is one thing that you should know about piezos. And well, there are many things you should know about piezos, but basically piezos can be used as contact microphones. They can also be used as triggers, like as sensors. And piezos actually generate their own electric signals. So you don't need to power them. Like just the fact that you're going to tap on the piezo because it has piezoelectric crystals in it, those crystals are actually generate power. Okay. And it's not going to be like dangerous or whatever, you know, like it's just that they generate power. And when we use them for audio, the amount of power they generate is so low that you actually need to use coaxial cables to plug them to something. And the reason why we use coaxial cables, and what is a coaxial cable? It's explained in the lab, you know, like, so I will let you read the lab, but it's basically a cable where you have a positive pin, and then you basically have the ground, which is wrapped around the positive pin. And the reason why you do this is because the ground is protecting the positive pin from potential electromagnetic disturbances, because it's linked to the ground and it's protecting it, you know, like, so it's also what we call shielded cables, you know, like, so basically coaxial cables is a very special kind of a shielded cable. And we need to use that with piezos because the signal that you create with the piezo is so low, like so tiny, that it can be very easily disturbed by any electromagnetic disturbances you might have in the room. You know, like power plugs, your smartphone, or whatever. You know, like they all create magnetic fields, and so that's why you want to use the coaxial cable. Then you're going to have to solder this jack connector to your Teensy audio shield to the microphone inputs. Okay, and you know, in the end, it's just going to look like this. You know, and now you know why my Teensy had this little guy. And then this will allow you to plug the piezo to the Teensy. Then you have a bunch of FAUST programs that sort of demonstrate to you how to use this setup. I will let you read this part. Now, I just want to talk very briefly about the assignments, which is make an instrument based on your Teensy, combining acoustic excitations captured in real time with a piezo to virtual resonator and audio effects. So that's what you will have to do. I will talk a little bit more about this on Wednesday. But on Wednesday, mostly I want to focus on OpenSCAD, which is the software that we're going to use with the 3D printers that you got as part of your kit. So do you have any questions